Welcome back. I promise this video is going to be fairly quick. I got a timeline I have to leave here in a little bit. We're going to go back to the piston pin offset. Now, the information I've shared with you, obviously I've received some negative comments towards and so on and so forth. So be it. The proof is actually in the pudding, not necessarily retaining to the V8s and the Chrysler practice of swapping the pistons around, so on and so forth. It goes even further than that. Something that is practiced within pro stock or elite type racing. Recently, within the last 24 hours, Tony Bishop from BES Racing released an instructional video talking about the different timing of the valves, the profile of the camshafts, the size of the camshafts, all the way up to 75 millimeter, and basically describing why the profiles of the camshafts are not necessarily about the older designs. Now, another individual that I've disagreed with, something I've called them out, and basically they have said, I'm completely wrong about it. They're a cam profile grinder, okay? Somebody in their shop or in their garage basically producing a product, and they'll start out with a blank, a traditional size cam core, and they'll remove material from the base circle. Now, by doing that, you can alter the lift and the duration of the camshaft, so on and so forth, with the final grind. But what we learned from NASCAR, even starting back as early as 1985 with Bill Elliott, when he set the speed at that time of, I believe it was 207 miles an hour, that was approximately when NASCAR started utilizing the larger cam core, the 55 millimeter. All of that was to increase the size of the base circle, realizing that the less aggressive ramp profile would allow the engines to operate at the extended RPM for a longer period of time without doing as much destruction to the engine. Now, that's being reinforced again with this instructional video from Tony, describing of the action of the valve actually opening. As everybody knows, as the piston is approaching top dead center, the clearance, the compression, the mechanical compression is the distance between the piston and the stationary object that's above it. But within that motion, from the time the piston is approaching top dead center, during the motion of the connecting rod moving within a crankshaft rotation to the point where the connecting rod is in the opposite direction, and the timing of when the piston reaches top dead center because of the location of the pin, depending on where that pin location is, it can either retard or advance when the piston is actually reaching top dead center in relation to the crankshaft degrees. Now, Tony had mentioned that within his research, so you don't have to take my word for it, somebody that has been very competitive with an Engine Master challenges, so on and so forth. I believe he's won a couple of times with multiple runner-ups against John Cossey, so on and so forth. And his entire cam or valve action was designed around that 72 degree mark. So 72 degrees of the crankshaft rotation for the downward motion of the piston is what he was shooting for. That is where the most velocity and volume of air can actually transition through the intake port. Now, from top dead center, the 72 degrees is your open window. Okay, that's if the piston is exactly at top dead center, the connecting rod and crankshaft are entirely in line. But you realize that the piston actually reaches top dead center differently with the offset wrist pin. In the advanced location, it causes the piston to reach top dead center sooner. In the retard position, the piston will reach top dead center later, in accordance to the actual crankshaft rotation, the position of the crankshaft. So to maximize the most amount of intake flow you possibly can get, is that as the piston approaches top dead center, is actually to start activating the opening of the valve before it reaches top dead center. Now, you also want to open the intake valve before top dead center because the exhaust valve is also open. So again, the timing of your exhaust valve closing, the piston reaching top dead center, and when the intake starts to open, we'll realize how much more airflow potential occurs before the 72-degree mark. Okay, so again, you don't have to take my word for it. You can go and tune in. I believe it was Engine Performance Seminar or Expo, so on and so forth. I'm sure if any of you just Google BES Racing or Tony Schiffoff, you're going to see his latest release. Now imagine if you have a cam that has a very small base circle. The aggressiveness of the cam load profile, as individuals are doing when they're grinding their cams, in order to achieve the largest lift, they're reducing the base circle and retaining the material above the cam core, increasing lift. You're also increasing the actuation of the valve, how severe and how fast it's opening. Even to the point where in the 1980s, NASCAR figured out by going to a large base circle, a larger cam, it allows those ramp profiles, the aggressiveness to be reduced and still provide an aggressive action within the valve. Now, the most precise cam load profile is one that delivers lift to the valve at the same exact ratio of the movement of the piston. You will not hear that anyplace else, anywhere. So as the piston is reaching top dead center, the valve should already starting to be opened. And as the piston is now traveling away, the ratio that the valve opens and the clearance between the piston itself should be as close together as possible. So the rate at which the piston moves down is the same rate that the valve can open. So now that has changed between a short connecting rod engine and a long connecting rod engine. And it also is affected by the piston pin location. Now, as Tony said, approximately in his testing, that he found out that most of the airflow occurs at 72 degrees. Why does most of the airflow occur at 72 degrees? What is occurring in the cylinder at that time? The most amount of vacuum in relation to the least amount of resistance. But is the airflow available before the piston even reaches top dead center? And what affects the amount of intake airflow before vacuum is being introduced into the cylinder? It is the exhaust gases leaving the chamber. So when the timing of the exhaust valve closing is not only in relation to the lobe centerline angle and where power is being produced, you want to take advantage of the timing of when the exhaust gases are creating the most amount of vacuum on the cylinder when the piston is approaching top dead center. Because again, at top dead center, there's very little vacuum from the actual mechanical movement of the piston. The vacuum being created, or the pressures in the chamber, is being created by the exhaust gases escaping. So if you have a very late closing exhaust valve, excuse me, making sure I got this, so I'm explaining this to you guys as simply as it can be. By having a late closing of your exhaust valve, majority of your high-speed exhaust gases have already escaped the cylinder. So you're not creating as much of a vacuum from between the exhaust and the new intake charge as possible. The timing of the fastest velocities, the actual exhaust impulse, while the exhaust gases are expanding in all different directions, the direction of flow is out through the exhaust pipes. And that body of mass has to be timed. You want to be able to take advantage of most of that air pressure as you possibly can. There's a window of time of when you can't open the intake exhaust because some of the you can't open the intake valve because some of the exhaust gases will actually back pressure into the intake port itself. But if you get on the back side of that exhaust impulse, it's actually creating suction, even while some of the gases are still expanding. It has a higher amount of negative pressures in the exhaust tubing that are in the cylinder. That timing is more important than your lobe separation angle, even though they're pretty much the same measurement. When you open the exhaust valve, in accordance to when the intake valve opens, is more important than the timing of the exhaust valve closing in relation to the crankshaft rotation and the piston location or movement. There's more power to be had from the exhaust side than most people get credit for. Now, some of these cylinder heads out there, depending on the valve angles, the overlap, and the position of the valves within relation to each other will determine how much flow can actually occur in that time frame. If you have a deeper pocket of the valve seat with a ridge that might protrude from the combustion chamber that blocks some of that shared vacuum from the exhaust gases onto the intake, it's helping direct more of those exhaust gases further away from the actual seat levels of both the intake and exhaust. So one of the things you can do is actually deepen, okay, without losing any power, like you would if you put all of your valves at the exact same plane in a wedge style chambered head. One of the things you can actually realize to increase power is to actually put the exhaust valve in the head a little bit deeper, because that vacuum is now being shared more towards the inside of the chamber or inside of the cylinder and not directly pulling sidewards on the intake. The pressure or the vacuum being created by the exhaust gases moving out cannot necessarily make that sharp turn into the intake port. It is shared more out past the intake valve seat arrangement. So as the intake opens, it's just like flagging an intake port. If you can put that string in there, you'll notice that the string will not necessarily curve around a very sharp area. Airflow will not turn a sharp corner. It needs to have a radius. So by having the valves exactly at the same plane, if this is the exhaust valve and it's closing, when the intake valve opens, the valve actually creates a radius between the two. Now, some of your intake gases are going to escape through the exhaust, or there's a possibility of the exhaust gases actually escaping and causing pressure or backflow into the intake system. By seating your exhaust valve deeper, okay, so it's the same motion, the same travel of the exhaust valve, but as the exhaust valve is getting past the intake valve, you can start opening the intake valve. And because of the sharper corner or any of the material in the combustion chamber protruding into the chamber, you can actually open the exhaust or the intake valve sooner without interfering with the amount of flow that the exhaust is actually pulling on the intake system. Very minute, but within most of the time it's 8 degrees, depending on the piston location, and up to 12 degrees in a typical situation. And your piston speed will dictate of how fast the valve opens in relation to the profile of the cam. So if you alter your connecting rod length, you can also alter the ramp profile of the cam, because it's about the speed of the motion of the valve as it is opening and the clearance between the piston. The more clearance you have between the valve and the piston, the faster you can actually open the valve, because as it is going into basically the top of the piston into your valve reliefs, if they are big enough, you can push the valve into that area before the piston actually starts moving down in its intake motion or intake stroke. Okay, so again, up till that point, the flow is coming from the exhaust, and how the flow is being exposed to the intake valve when it's opening will deliver a different performance level, period. So the machining practices are typically, they're about uniformity, not necessarily towards performance. How many of you know that a machine shop that will actually allow the exhaust valve to be seated deeper into the combustion chamber than the intake? And how many of you have seen a machinist to where the seat of the intake valve allows the intake to hang out past the exhaust valve? What is occurring between the two events? And the closer the intake valve is seated within a combustion chamber, the closer it is in relation to the piston. It's all very small timing aspects, but if you can optimize all of those timing aspects, there's additional power in that combination. That's also going to dictate your actual valve angles. 45 degrees is the industry standard, but does that necessarily create the best flow characteristics from your seat configuration? It depends on the cylinder head, the timing of the valve openings, and the relation of both the intake and exhaust valves when they are in that transition period between exhaust and intake. It's a game of timing. You also don't want to open the exhaust valve too soon because there is still pressure building in the cylinder. Has that been accomplished to the point where the explosion of the combustion process and the loss or the expansion of combustion pressures pushing the piston down? Is there a peak point in the where it starts to dive off? Can you then open your exhaust valve? Yes. So the added duration to an exhaust or to a camshaft profile, like a dual pattern camshaft, they will almost always benefit horsepower. But they're allowing the pressures of the cylinder and the combustion to bleed off before the piston reaches the bottom of its rotation in the travel. That timing is going to be associated directly to torque. So again, if you're building a high performance, high horsepower engine designed and taking advantage of the higher RPM, you need to have that earlier exhaust valve opening. But again, the closing time has to be dictated by when the exhaust gases are escaping the exhaust port and when the intake is starting to open. Because once again, if you close the valve too soon, there's not going to be as much vacuum pulling the intake charge in. If you close it too late, beyond the point where your exhaust gases are actually escaping into the exhaust, it's not going to have as strong of a signal to pull on the intake charge once the intake valve opens. It's all about timing, and that also changes within the RPM band. That's what makes camshaft profile specific to a certain power band. It's the timing, not only from the LSA or the valve action, it's also within all the other relations to that. So if you're working with a combination, let's say a just standard 350 Chevy, the engineers have already tested all of this. So most of the components you'll find in camshaft profiles have already been tested with that amount. Can you find additional horsepower by modifying those components or changing the timing? Yes, you can find additional horsepower. But you're still stuck to a power band that has been determined already within testing. So if you're buying a camshaft with a 3,000 to 7,000 RPM range, there are mechanical things within the design, whether it be cubic inch, connecting rod length, valve sizes, that will overthrow and dictate whether or not that power band is either expanded, narrowed, or shifted within the power band. It's all about timing. Hopefully that helps out. Have a good one.